Welcome back, Signals and Systems experts. We're talking about properties of the discrete-time Fourier transform. Let us continue. All right, so the next up on the list is the convolution property. The convolution property says the following. Suppose x of n has Fourier transform capital X of e to the j omega, and y of n has Fourier transform capital Y. And what we see is that the convolution of x with h in time is the same thing as what we saw in continuous time, just so important that it's restated here. It's the multiplication. So the two consequences to this: number one, the computationally expensive operation of convolution can instead be done in the frequency domain with just multiplication, regular old multiplication. So that's good. So we can, if asked to do a convolution, we can take the Fourier transform of both of those signals, multiply them together, then take the inverse Fourier transform to get back the signal. And the second important point here is that this gives rise to filtering, because again, the engineering part of this is that if we have a linear time-invariant system and we put in x of n and the system has impulse response h of n, then what we get out is x of n convolved with h of n. So we know that in frequency, then this would be x times capital H, which is the frequency response. So again, if the frequency response is 0 or close to 0 for some frequencies, then those frequencies get scaled by 0 or close to 0, and so they get filtered out of the system. So it's this convolution property that gives rise to the concept or the idea of filtering. And I just want to point out convolution property because in time we're convolving. So the name of the property is what you're doing in time, which is convolving. Okay, so then, not to be outdone is the multiplication property. And the multiplication property says this: suppose that x of n has Fourier transform capital X and y of n has Fourier transform capital Y, then the Fourier transform of the multiplication of those two signals is the periodic convolution. So I'm going to represent the periodic convolution with kind of a circle there. So I'm just, oops, no, sorry, let me back up. This is not x of n, it's capital X of e to the j omega, and a circle. The periodic convolution is something that we talked about with discrete-time Fourier series. So I'm just going to note this is the periodic convolution. So what was the difference between regular convolution and periodic convolution? I will write it out here. We take both of these functions, versus frequency, and we plot them versus a dummy variable. So I'm going to call theta that dummy variable. Then we flip one of them and shift by the variable, integrate over the variable. So that was regular convolution, and the periodic convolution is you only integrate over 2 pi. So this is periodic convolution. So other than that, though, that is the same as continuous time, where you multiply, right? The multiplication property is what you're doing in time. So you multiply in time, and that's the periodic convolution. I'm missing a 1 over 2 pi. So it's 1 over 2 pi times the periodic convolution. So this is, again, the multiplication in time is 1 over 2 pi times the periodic convolution in frequency. And so finally, I do want to point out that, again, these are similar to continuous time, but also here's the duality principle in action, right? Convolution in time is multiplication in frequency. Multiplication in time then is convolution in frequency. So there are these dual pairs that we've been talking about. So this would be a dual pair, convolution and multiplication. Now, these are not the entire list of properties, and there are other properties that we are not covering that are similar to what we saw in continuous time. And you should be aware of these properties. They're listed in a table any textbook or on the internet. So keep in mind all these different properties, like linearity we didn't explicitly cover here, or the time shifting property we didn't explicitly cover. So those are all summarized in tables in textbooks and the internet. So how about let's look at those tables then.